Hello, I'm Alan Rosas, and in this video I'm going to be solving two problems from section 12.1 of James Stewart's Calculus Early Transcendentals. So the first of these problems is number 42, and it's from the problem set 27 through 42, all of which are given the statements, describe in words the region of R3 represented by the equations or inequalities. The next problem we're doing is from the set 43 to 46, and these read, write inequalities to describe the region, and the one we're doing gives us the description, the solid upper hemisphere of the sphere of radius 2 centered at the origin. So these problems are kind of backwards from each other. In this problem, we're given an inequality, and we need to describe the region it represents using words. Whereas with this problem, we're given a description of the region in words, and we need to produce an inequality that represents that region. So without further ado, let's go ahead and get started with problem 42. Okay, so whenever I see inequalities like this, and in particular, the things I look for are these x squared, y squared, and z squared terms, as well as some z terms. Or let me backtrack. When I see this x squared, y squared, and z squared, especially when they're added up like this, the first thing I think is this could be maybe a sphere, maybe it could be or something else. But the thing that kind of gives that away for me is that when you sum up these squares, you get some kind of distance, right? And especially like if you take the square roots, then this is the distance from the origin. What this means, therefore, is that if this right side were 0, then here, let's pretend for a moment. If this right side were 0, then this region would represent all of the points in R3 whose distance from the origin is positive. And so it's not too difficult to see that this would be every single point in R3 except for the point that has a distance equal to 0 from the origin, namely the origin itself. But we're not given this right side for this problem. Instead, we have this 2z here, and as soon as I see this 2z, one thing that sticks out to me is the idea of completing the square. Now, as a quick refresher for anyone who might have seen completing the square but doesn't quite recall it completely, it's a way for us to be able to solve quadratic equations by hand. And more generally, for us to be able to rewrite, let me erase this, rewrite a quadratic like this in the form a x plus or even minus some number b prime, call it, squared, plus some other number c prime. And essentially, why this is important is because we can get all of the x terms under a square, except perhaps by adding or subtracting by some constants, and then we get some other constant on the outside. And this procedure is actually a way for us to actually prove the quadratic formula, but I won't get into that here. For now, let me give a quick reminder for how this works. Erase. So the first thing we're going to do is we're going to factor out the a from everything here, the leading coefficients. So now, all we need to do is worry about this polynomial right here. And the trick to writing it in the way that we want is to take this coefficient b over a, divide it by 2, So we're going to take this coefficient, we're going to divide it by 2, which I'll denote like this. So this is b over 2a. And then we're going to square the result. So we're going to get b over 2a squared. And whatever number we end up with at the end, what we're going to do is we're going to add and subtract that number to this expression right here. Doing so, we got x squared plus b over ax plus b over 2a squared plus c over a minus b over 2a squared. So here I've added b over 2a squared and subtracted the same amount. And the reason for doing this is because this whole left side right here actually factors as x minus b over 2a squared. I'll leave that for the viewer as an exercise to verify. And so what we get is exactly what we wanted. We got x, remembering that we have the constant a at the front, we get x minus b over 2a squared plus c over a minus b over 2a squared. And then we just need to multiply throughout by a to get the result that I wrote at the beginning. So that's a quick refresh on completing the square. Why am I bringing this up here? Well, we're going to use the same technique to rewrite this inequality here in a more convenient way that will immediately reveal to us what it represents geometrically. So first thing I'm going to do is I'm going to get any terms with the single power of our variables x, y, z. So here we have z to the power of 1. And I'm going to move them over to the left side here. So I get x squared plus y squared plus c squared minus 2z is bigger than 0. Now, the thing we want to complete the square on are these z terms right here, because this is a quadratic, but it's not in the form that I wrote earlier, where it's just x minus some number, possibly all squared, plus another number. And so here, running the procedure of completing the square, well, we're going to take this coefficient for z, and just like we did here, we're going to divide it by 2, so that gives us -1, and then we're going to square it, which is just 1. And that's the thing we're going to add and subtract by. So add 1 minus 1, this is bigger than 0. And so this factors as z minus 1 squared. And if we bring over this, if we add 1 to both sides to get rid of this constant, our inequality becomes, x squared plus y squared plus z minus 1 squared is bigger than 1. And some of you might already see what this represents. To make things a bit clearer for us, let's go ahead and take square roots on both sides. Now, square root of 1 is just 1, so this is just equal to 1. And the left side here, you might notice, is the distance. Let me write this down. From the point xyz to the points 0, 0, 1. So our inequality is describing, let me write this in words. Thus, the inequality represents all points x, y, z whose distance from 0, 0, 1 is strictly bigger than 1. And we have the strict inequality here because of this strict inequality. And hopefully everyone agrees that this region is just all of R3, but with the inner sphere centered at, or inner ball centered at 0, 0, 1, deleted from the region. And I'm going to give you guys a 3D representation using software of this region so that we can get a better feel like for what this looks like, and to confirm what I just said, which is that this is all of R3, all of space R3, but with the ball of radius 1 centered at 0, 0, 1 removed. Okay, let's hop on over to my 3D graphing calculator. I will see you guys there. Okay, so here we have a plot of our regions. And I know it's hard to kind of see what's going on. The problem here is that the software I'm using, it's Graphical on the Mac, fills in regions via inequalities using these little spheres. So the idea here is that anything that is to be represented by, for example, I just turned off the red region. So now this only leaves the blue region, which is our region of interest here. Notice that we have the same inequality. The square roots of everything here in the inside is bigger than 1. And so any part of the diagram that's filled in with the blue sphere is supposed to indicate a region where the points in that region belong to the, or solve the inequality. Now there's a few gaps between the spheres. That's just because this program doesn't have unlimited precision. But if we zoom in, we can see that there's a hole right here. And the axes are a bit hidden right now, but if we turn down the size just a little bit, we can see this would be the x-axis, y-axis, and z-axis. And turning up the size again so that all of these little spheres don't mess with us too much, we can see that there is a hole right here, x-axis, y-axis, z-axis. There's a hole up towards the positive z-axis. And we can reveal this hole further, what this hole is, by plotting the other region I filled in. So there's only two possibilities. Either our point has a distance bigger than 1, in which case we solve the first inequality, or our point has a distance smaller than or equal to 1, in which case we have the second inequality. And if we plot the second inequality, we see that this missing hole corresponds to everything that was removed from the inequality up here. And zooming out once again, we see that, in fact, this region right here, the blue, is it's all of space, R3, minus this sphere centered at 0, 0, 1 with radius 1. And here, just once again, to emphasize this sphere right here we can turn down the size of the spheres a bit just to see what's better going on. And we can do the same thing with this other region, turning down the size just a little bit. And so if we zoom in once more, again, we have the same thing we observed earlier. Okay, so in summary, the region represented by the blue, which is, again, we obtained by solving our original inequality, represents, in words, all of space R3 minus the ball centered at the point 0, 0, 1 with radius equal to 1. Okay, Let us now do problem 46. So here we're going to go backwards. We're given the region described in words, and we need to write inequalities that describe that region. So once again, here the region of interest to us is the solid upper hemisphere of the sphere of radius 2 centered at the origin. Okay. So already, when I hear sphere of radius 2, and also with the fact that it's centered at the origin, I'm already going to create an equation for this. So the sphere of radius 2 centered at the origin has this equation here. Note that, oh, this is supposed to be a z. And I was going to say, note that that should have been a z. I just cleaned it up. Or that should have been a 2. I cleaned it up because it looked too much like a z. Okay. So now we have this sphere of radius 2 centered at the origin. But note that they say, and this is important, they want the solid upper hemisphere of the sphere. So the fact that we need to include the solid means that, so let me sketch out a sphere really quick. Let me sketch out our sphere. So this is x-axis, y-axis, and z-axis. And the radii here are 2. Because they want the solid upper hemisphere, in particular they want the solid region, what we need to fill out is everything that's above the xy plane, because we want the upper hemisphere. And so if we draw out what this region should be, this would be everything right here. But what is this region? Well, just from the sketch, hopefully everyone agrees that any points up here must have z coordinates bigger than or equal to 0, because the points whose z coordinate is equal to 0 all lie on the plane, the xy plane. And so if we want to be above the xy plane, we need to have a z coordinate bigger than or equal to 0. So let's include this as a condition, as an inequality. And finally, to get the fact that we want this to be solid, we just need to make sure that our equation here includes every single point that's not just on the surface of the sphere, which as written would mean that we have this equal sign here, but also everything inside. And to get that, we just need to add on a less than or equal to right here. One way to see this is that if you pick a point up here, say XYZ, then because it's in the inside of the big circle, we know that the distance from XYZ to the origin, which if you'll remember is just square root x squared plus y squared plus z squared, this has to be less than the distance from the center of the sphere to the outside, which is 2. So we get this inequality. And to make sure we include the boundary of the sphere as well, we tack on this less than or equal to, which is equivalent to this inequality here, just by squaring both sides. So in summary, the inequalities that describe this region are x squared plus y squared plus z squared is at most 2 squared, together with z bigger than or equal to 0. Okay, that's it for this video. If there's any questions, please feel free to leave a comment. Otherwise, I will see you all next time.